Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to talk on the module Mesoscopic Physics from the paper Physics at Nanoscale. So the learning objectives of this module are: first, we will discuss the mesoscopic transport in 1D. Secondly, we will also discuss about the mesoscopic thermal transport. So students, let us start with a basic introduction about the module. Small scales required for confinement. Why is it so? So if an electron is trapped inside an atom or a quantum dot, it can be treated like a problem of an electron in deep potential well. The constraint for this is that the electron should not exist outside the atom of a quantum dot. So here the electron behaves as a wave. So the quantization rule for the wavelength and the energy applies. This makes the wave function associated with the electron into an atom or a quantum dot be zero at the boundaries. Therefore, the electron with the wavelength lambda, the characteristic dimension d should not be less than, that is, d is equal to lambda by 2. Thus, lambda will be equal to 2L. So, d is approximately equal to L. Now, what would be the diameter of a copper quantum dot to hold an electron in the ground state with the energy equal to 5 electron volt, that is the Fermi energy? The energy of an electron in a deep potential well of characteristic dimension is given as E is equal to pi square h square divided by 8m d square, where n is equal to 1, 2, 3, so on. For ground state, n is equal to 1. Now here pi is removed by n. So the characteristic dimension is given by, that is d is equal to root of h square by 8me equal to, putting the value of h equal to 6.63 multiplied by 10 to the power minus 34 joule second, 8 and the value of m for an electron is 9.1 multiplied by 10 to the power minus 31 kg, and the value of E, which is given over here, that is 5 electron volt. Now converting it into joules, we multiply it by 1.6 multiplied by 10 to the power minus 19 joules. We calculating this, so we get D is equal to 2.73 multiplied by 10 to the power minus 10 nanometer. So certainly the size of a quantum dot should not be smaller than the atomic size. Metal to insulator transition. Electron confinement is possible by reducing the dimensions of the solid to the order of spacing of atoms in the solid. So students, it is possible which the nanomaterials make and possess the dimensions for electron confinement. The average spacing between the occupied space is delta E is equal to 4 EF divided by 3 NV, where EF is the Fermi energy and NV is the total number of valence electrons. So small be the size of atom, fewer valence electrons, larger be the spacing between the energy states. So students, we have successfully converted the metal at nanoscale into the insulator. So students, continuing our discussion over metal to insulator transition, quantum confinement is the phenomena which makes the transition first from metal to semiconductor and then from semiconductor to the insulator. So as it is evident from this figure, which shows the energy levels for the sodium atom, if there are 13 atoms, which is equivalent to 13 valence electrons, and 13 energy levels are between the 0 and the Fermi energy. So electrons within the kBt of the Fermi energy, they can conduct. This is schematically shown in the zoomed figure. If delta E is greater than kT, the electrons remains below the Fermi energy and do not conduct. So now to conclude that quantum confinement can be achieved either the particle is very small or the temperature is low enough. So students, let us now discuss this topic by taking an example or a problem. What should be the size of the silver particle to achieve quantum confinement at room temperature, that is around 27 degrees Celsius, where the Fermi energy level is equal to 5.5 electron volt. In order to achieve the quantum confinement, the energy spacing should be delta E is equal to 4 EF divided by 3 NV must be greater than kT, where the number of valence electrons must be less than 4 EF divided by 3 kT. Now putting the values of EF, that is 5.5 in the case of electron volt, to convert it into joules, we multiply it by 1.6 multiplied by 10 to the power minus 19, and this putting the value of kB as 1.38 multiplied by 10 to the power minus 23, and the temperature as 300 Kelvin. Now the electronic configuration of silver is Kr 4d10 5s1, that is 1 electron per atom. Now the density of silver is 10,490 kilogram per meter cube and atomic mass is 107.9 gram per mole. So the density of atoms is the density of silver, that is 10,490 multiplied by the Avogadro's number, that is 6.02 multiplied by 10 to the power 23 atoms per mole, divided by the atomic mass, that is 0.1079 kg per mole. So this is equivalent to 5.85 multiplied by 10 to the power 28 atoms per meter cube. Now the volume of particle with 283 atoms is Vp, which is equal to 283 atoms divided by 5.85 multiplied by 10 to the power 28 atoms per meter cube. This is equal to 4.83 multiplied by 10 to the power minus 27 meter cube. Now if we'll assume the particle to be a perfect sphere, the radius of the particle is r is equal to 3 Vp by 4 pi to the power 1 by 3, approximately equal to 10 to the power minus 9 meters. So the silver particle will behave like a non-metal if its diameter is less than 2 nanometer. Band gap and size dependence. So students, as you can see from this figure, as we are decreasing the size of the material, there is an increase in the band gap. So if we have a solid, there are closely spaced energy sublevels corresponding to energy bands. If we go to nanoparticle, then we have distantly spaced sublevels. It increases the band gap. Now we have removal of few atoms, that is distance between the sublevels increased. So hence we can tune the electronic and optical properties. So students, let us now discuss the mesoscopic physics. Mesoscopic physics deals with the intermediate region between the macroscopic and either micro or nanoscopic world. It is mostly applicable to the objects between the nanometer to micrometer length scales. In the case of transport of charge carriers, it deals where the dimension of the object is more than the free path but less than the phase coherence length. So macroscopic conductor is the one when we have Le less than equal to L phi, less than equal to Ln, and very much less than L. And if we have the mesoscopic conductor, Le is less than, very much less than L, very much less than L phi, and less than equal to Ln, where L phi, Le and Ln are the phase coherence length, mean free path between elastic scattering length, and the distance traveled by the electron after losing energy kT respectively. So the electron transport depends upon the reduced dimensionality, which is clearly shown in this figure, that if we are confining the electron motion in at least one spatial dimension, affects the energy levels and the density of states. So if we'll have a bulk, then the density of states varies continuously with the energy. For a quantum well, it shows a step-like behavior. For a quantum wire, it is both the discrete and the continuous. But for a quantum dot, it is like a delta function. So let us now discuss this by taking the example of a conductor. Now according to Ohm's law, consider a current carrying conductor. According to the Ohm's law, the R is related to the cross-sectional area A and the length L by the relation R is equal to rho L by A. So students, this figure shows the schematic of the current conduction through a conductor in the different dimensions. That is, in 3D, the length of the conductor is more than the inelastic mean free path L phi. Hence, the conduction is diffusive. In 2D and 1D, the length of the conductor is less than L phi. So, the conduction is ballistic. Now, we know that the reciprocal of the resistance is the conductance, and it is given by G is equal to sigma A by L. So now, if we reduce the length of the channel by half, the resistance would go down by half. But what if we reduce the length to a very small dimension, let us say 0? Will the resistance tends to 0 and it becomes a superconductor? Conventionally, when an electron passes through a solid, it follows a random path traveling in one direction for short interval of time and then scattered in other direction. This is called diffusive transport. What will happen if the inelastic mean free path of an electron is more than the dimension of the wire? The electron will pass through the wire without suffering any scattering, just like a bullet. This is called a ballistic transport. Mesoscopic transport in 1D. Whenever the dimension of the system is less than the inelastic mean free path L phi, the current conduction mechanism in a conductor has to be treated quantum mechanically. In a quantum conductor, the resistance through a wire connecting between the two electrodes can be given by the Landau formula, which is R is equal to H by 2E square mt, where T is the transmission probability through a scatter in a conductor, and the above equation can be written as R is equal to H by 2E square mt plus H by 2E square m, the whole multiplied by 1 minus T by T. Now here, the first part, which does not contain T, is called as the contact resistance. However, the second part is the actual contribution from the conductor. And this figure shows the schematic of a current carrying conductor as a barrier with transmission probability T. The total resistance is the sum of the contact and actual resistance of a wire. Now, continuing our discussion over mesoscopic transport in 1D, let us solve the Schrödinger equation for a conductor in 2D. Then, the time-independent Schrödinger equation of a current carrying wire is given by E0 plus px square by 2m plus py square by 2m multiplied by psi xy is equal to E psi xy. And the energy eigenvalues are E as a function of kx, ky is equal to E0 plus h cut square kx square by 2m plus h cut square ky square by 2m. Now in this case, the energy is quantized along z direction as the conductor is reduced from 3D to 2D. In this figure shown on the left hand side shows the schematic of the current carrying conductor in 2D, that is without base bias and with gate bias. Now in the presence of gate bias, the Schrödinger equation takes the form, that is we add one extra term, that is Vy, where V of y is equal to half m omega naught square y square. And corresponding to this, we have the energy eigenvalues given by E naught plus h cut square kx square by 2m plus n plus half multiplied by h cut omega naught by 2 pi. In this case, energy is quantized along y and z directions. The energy is quantized along y direction due to gate bias. The second term is simply the contribution of free electrons along x direction, and En is equal to E naught plus pi square h cut square by 2m multiplied by nx square by L square plus n plus half h cut omega naught by 2 pi. So the third term in this equation decides the number of conduction channels along the x direction. Now let us consider the electron having energy E. The channels with energy greater than E are not allowed, however the electrons will traverse through the channels below the energy E. Since the barrier height increases with the channel index, there are always be the finite number of channels which are open. So the number of open channels in the mesoscopic conductor is given by Me is equal to summation over n of E minus epsilon n. So hence the total current carried by the channels is given by I is equal to 2 small e by h m multiplied by mu r minus mu l equal to 2e square by h m multiplied by mu r minus mu l by e, where mu is the chemical potential or the Fermi energy at zero temperature. And here mu r and mu l are the chemical potentials of the right and the left contacts respectively, as shown in this figure. Now Gc is equal to 2e square by h multiplied by m. It is clear that more be the gate voltage, the less be the number of channels and hence the conductance, as m can take only the integral values. So Gc is quantized. It is noted that Gc does not depend on any material parameters. So here in this below graph, the variation of Gc with the Vg voltage is shown with the variation in the temperature. That is, the conductance shows plateaus at the multiples of 2e square by h. It is clear that more be the gate voltage, the less be the number of channels and hence the conductance. Mesoscopic thermal transport. So students, as discussed before, that generally mesoscopic phenomena in transport processes occurs when the coherence length of the carriers become larger than the sample dimensions. When two reservoirs are connected by quasi one-dimensional mesoscopic conductor, electrical conduction becomes quantized and the conductance of the conductor is determined by the number of participating quantum channels, and the conductance is given by Landau formula. So the similar behavior should be applicable for heat transport in mesoscopic phonon system. The maximum heat current for a single channel can be derived by Landau formula for elastic transport between two electron reservoirs L and R. JTH is equal to minus infinity to infinity the integral over d epsilon by 2 pi h cut multiplied by epsilon t as a function of epsilon multiplied by FL as a function of epsilon minus FR epsilon, where F as a function of epsilon is the Fermi function of the reservoir, where this A is equal to L and R, and T epsilon is the transmission function. Now the thermal conductance is given in both the cases integration by GTH is equal to JTH by delta T, which is equal to, that is the quantum thermal conductance is equal to G naught, it is equal to pi square K square T by 3H. This is the maximum possible value of the energy transported per phonon mode through a mesoscopic thermal conductor. This is also amazingly results that quantum thermal conductance does not depend on the statistics. Quantization of thermal conductance. So this figure, the students note over here that this shows the experimental proof of the quantization of the thermal conductance. So thermal conductance has the limiting value, that is G naught is equal to 9.456 multiplied by 10 to the power minus 13 watt per K square T. So this shows the quantization of thermal conductance for temperature above TCO less than 0 to K Kelvin. A cubic power law behavior consistent with a mean free path of 0.9 mm is observed. For temperatures below TCO, saturation in GTH at a value near the expected quantum of thermal conductance is observed. So students, let us summarize what we have learnt in this module. First, the mesoscopic physics that deals with the intermediate region between macroscopic and either microscopic or nanoscopic world is mostly applicable to the objects between nanometer to micrometer length scales. Secondly, whenever the dimension of the system is less than the inelastic mean free path, the current conduction mechanism in a conductor has to be treated quantum mechanically. Thirdly, after solving the equation, basically the Schrödinger equation, the electron has energy E. The channels between with the energy greater than E, they are not allowed. However, the electron will traverse through the channels below the energy E. Next, we discussed that generally the mesoscopic phenomenon in a transport process occurs when the coherence length of the carriers become larger than the sample dimensions. Lastly, when the two reservoirs they are connected by a quasi one-dimensional mesoscopic conductor, electrical conduction becomes quantized and the conductance of the conductor is determined by the number of participating quantum channels, and the conductance is given by the Landau formula which we have discussed. Thank you.